Very nice. Welcome to the quantum classes by Bhartiya Kisan, Indian farmer, and Ayavarth Krisaka. And today we are going to discuss about the thought experiment, that is a next thought experiment, single slit diffraction experiment. So for it, let's consider a highly collimated beam of photons moving along the x direction. Such that P sub x equals to P naught equals to h by lambda and P sub y equals to 0. Let the beam be incident upon a single slit of width d as shown in the figure. The photons are diffracted by the slit and the diffraction pattern is shown. Since the slit is of finite width d, the position of the photons along the y direction is uncertain by an amount d, that is delta y equals to d. The position, what can we say about the component of their momentum in the y direction? All we know that is the photon will arrive at the screen somewhere within the diffraction pattern, but we don't know where. Thus the uncertainty in momentum is given by the angular spread of the pattern. Angular spread of the pattern. Since most of the photon hit the screen within the central maxima, we can obtain a rough estimate of the spread in P sub y. That is delta P sub y. By confining ourselves to the analysis of the central maxima, from figure we can see that for the central maxima P sub y can take values ranging from minus P naught sine theta to P naught sine theta. Therefore, delta P sub y equals to 2P naught sine theta. Now, we know from the diffraction theory that the angular spread of the pattern is inversely proportional to the width of the slit. Hence, sine theta equals to lambda by d equals to lambda by delta y. Here lambda is the wavelength of the incident beam or light. Hence, we obtain delta y, delta p sub y equals to d into 2p naught sine theta equals to 2p naught lambda, or delta y into delta py equals to 2h, since lambda equals to h by p naught. This is consistent with the uncertainty relation delta y, delta p sub y greater than equal to h cut. Trying to reduce the width of the slit to reduce delta y leads to a greater spread of diffraction pattern, increasing the momentum uncertainty. Thus, it is impossible to measure the position and momentum of a microscopic particle precisely at the same time. Finally, next we are going to describe the double slit experiment. It is also a thought experiment, which is another milestone in establishing the uncertainty principle. Now, for double slit experiment, let's consider. Now, here we are going to discuss about the double slit experiment. So, in the double slit experiment, a beam of monoenergetic microscopic particles such as photon, electrons, protons, etc. are allowed to pass through two slits, slits 1 and slits 2, two slits before falling on a fluorescent screen placed nearby, as shown in the figure. If after some time we plot the total number of particles arriving at the screen as a function of position, we observe an interference pattern. This is a characteristic of waves and can be explained as follows. The matter waves corresponding to the particles are split at two slits and then interfere with one another. But beware of thinking of these matter waves as a classical waves, because particles do arrive at the fluorescent screen in a particle-like way. We got one localized flash every time a particle strikes the screen. However, the totality of a spot made by a large number of particles look like the wave interference pattern, but then is of wave-like behavior seen only when we observe a group of particles. What happens when only one particle arrives at the slit? The answer to this question: suppose we make the particle beam very weak so that at any one instant only one particle arrives at the slit. Do we still get an interference pattern? Quantum mechanics says yes to this, and experimental data seems to agree with this viewpoint. It is not easy to accept this picture. You may ask, can a single particle split pass through both slits and the two halves interfere with one another? Quantum mechanics says yes to all these questions. As Paul Dirac, one of the pioneers of quantum mechanics, put it, each photon or microscopic particle interferes only with itself. Why don't we find out whether it is correct by making a measurement? The simplest way of doing this is by the means of a thought experiment. Look, with a flashlight, we can focus a flashlight on the slits to see which slit the particle is really passing through. What do we obtain? We find that the interference pattern is destroyed. How do we explain this effect? This effect can be explained by the uncertainty principle. As soon as we try to locate the particle and determine the slit, that is A or B, through which it is passed, we lose information about its momentum. As we have seen in the gamma ray microscope experiment, the collision of the particle with photon we are using to observe it affects its momentum and introduces an uncertainty in it. Mathematically, to observe whether the particles goes through one of the slit, the photon wavelength must be smaller than at least half the distance d between the slits. Now delta y less than d by 2, therefore its momentum h by lambda must be larger than 2h by d. As per the de Broglie relation, the interaction of this photon with the particle will make its momentum uncertainty by an amount delta p. Amount delta p sub y given by the uncertainty relation. This uncertainty in the particle momentum introduces an uncertainty in its position on the screen as shown in the figure. Now it is given by delta y by a equals to delta p sub y by p naught greater than equal to 2h cut by tp naught, or delta y by a equals to lambda p by d pi. since delta y into delta p sub y greater than equal to h cut and delta y is less than d by 2. Hence delta y greater than equal to a into lambda sub p divided by d into pi, where lambda p equals to h by p naught is the de Broglie wavelength of the particle. Now the condition for constructive interference is d sine theta sub n equals to n lambda sub p, so that the distance between two adjacent maxima is y sub m equals to a sine theta sub n plus 1 minus a sine theta sub n equals to a lambda sub p divided by d. Thus we get delta y greater than equals to y sub m divided by pi. In other words, the uncertainty in position of the electron produced as a result of attempting to detect it near the slit is of the order of the distance between the two adjacent maxima. This uncertainty is enough to shift the interference pattern observed at the screen up and down in the y direction by a distance roughly equal to the distance between two maxima. Such a random shift is just enough to smear out the interference pattern so that no interference is observed. So if we attempt to determine the slit through which the particle passes, the interference pattern is destroyed. The fact of matter is that as soon as we lose information about the particle's momentum, we must also lose information about its wavelength, as per de Broglie relation. But if there were interference fringes from fringe pattern can interference fringe from their spacing, we would be able to measure the wavelength. Thus the fringe pattern cannot exist anymore. The interference pattern is destroyed. Now let's discuss about the complementary principle. The point is that the position and momentum measurements are really complementary. As Bohr first pointed out, they are mutually exclusive process. This means that we can concentrate on the momentum and measure the wavelength of the particle from the interference pattern and hence its momentum. But then we cannot tell which slit the particle went through. Or we can concentrate on the position and lose information about the wavelength and momentum. You have seen that when we try to find out which slit the particle passes through, we lost the interference pattern and hence the information about its wavelength and momentum. In his complementarity principle introduced in 1928, Bohr described this situation by stating that wave and particle aspects of a physical systems are complementary. When we localize, that is, find out which slit the particle goes through, we reveal the particle aspect, and when we don't localize, don't worry about which slit the particle goes through, we reveal the wave aspect. However, we cannot reveal both the aspect at the same time, and they are complementary. We may well ask, is it the microscopic particles are both wave and particles and we can see only one attribute with a particular experiment arrangement? That is, they possess well-defined position and linear momentum at each instant, but we are unable to measure them simultaneously. Or is it that the particles just do not possess well-defined position and momentum simultaneously? While Einstein was of the former view, which he never gave up, Bohr and Heisenberg took the latter viewpoint. Their interpretation of the quantum mechanics is also referred to as the Copenhagen interpretation. Thus, the uncertainty relation propagates the view that these uncertainties arise as a result of an inherent limitation of nature. These are intrinsic to the nature of the quantum world. However precise may be the measuring devices, one method of measurement, there is no escape from these uncertainties. The Heisenberg uncertainty principle is clearly a consequence of wave-particle duality. It reflects the fact that quantum mechanics, although a complete theory, provides a less detailed description of a physical system than does classical physics. This description is governed by the complementarity principle. The uncertainty principle is a fundamental principle of quantum physics. You have noticed the role of Planck's constant. It is so small that the limitation imposed by the uncertainty principles are significant only in the domain of microscopic particles, namely atoms, molecules, subatomics, nuclear and subnuclear particles. On this scale, however, this principle is of great help in understanding many phenomena. Let us see some interesting application of this principle in the next lecture.